So I'm pleased to have been invited to talk to a number of you. I think I see your names on the screen. Um, my name is John Delaney. I'm a professor at the University of Washington in Seattle. My background extends back about 45 years. I started out as a mining geologist. Got involved in a program that involved living 6 months in the Galapagos Islands back in the 1970-72 time frame. Finished a dissertation at the University of Arizona where I extracted the gases from the glassy rinds of pillow basalts, which are lava buds, basically. They're about the size of anywhere from the size of a baseball to the size of 5 times the size of a basketball. Huge deposits of lava on the seafloor. When the lava comes out, it freezes instantly, within seconds. The outer rind does, and it traps the gases that were dissolved in the volcanic edifice in the magma. And I spent quite a bit of time extracting those gases and assessing what their compositions were. Following that, I took a job at the University of Washington in Seattle and in 1977, and within a year was involved in seagoing programs to the Mid-Atlantic Ridge with some of my colleagues from Woods Hole Oceanographic. And then in 1980, participated in my first Alvin dive to the seafloor on the Mid-Atlantic Ridge south of the Azores. And it was an absolutely magic moment for me, and I wound up basically becoming utterly enthralled. By that time, I had already captivated by volcanoes and became enthralled with underwater volcanoes. So the remaining time, is mostly in my career, is focused on studying and understanding underwater volcanoes and the hydrothermal systems that they support. That was just about the time that submarine hydrothermal systems were recognized in the Galapagos area, and then again at 9 North on the East Pacific Rise, not far south of Baja California. I was involved in developing with a number of my colleagues a program called RIDGE, which stood for Ridge Interdisciplinary Global Experiments. And that set in motion a 20-year program which was focused on the study of mid-ocean ridge phenomena, broadly speaking, from the physics, the chemistry, the biology of the 70,000 kilometer long ridge crest that stretches around the world like the strings on a baseball. So that was my introduction, in a sense, to the world of marine geology. And during the development of that RIDGE program, I dove again many times with my colleagues in Alvin, the submersible, and sometimes used remotely operated vehicles, sometimes used Navy vehicles, and dove to the seafloor and was fascinated to have multiple opportunities to study submarine hydrothermal systems. Some of the very exciting things that we found involved overhanging ledges where fluids had jetted out of a black smoke or chimney, and creating ledges, and water was trapped beneath those ledges and was an upside down reflecting pool, if you like. 250, 300 degree water was caught under this overhanging ledge in a pool, and we began studying those pools. We called them flange pools, and they were really quite fascinating because the boundary between the 250 degree fluid, which you could look up at and see a mirror surface which was rippling, that became a test bed where we did a number of experiments working with a number of different colleagues, including Russ McDuff of the UW. But I was frustrated by the process of studying underwater hydrothermal systems from the inside a submersible. It's a titanium hull that's about 2.5 inches thick, with very thick, almost 4-inch thick windows. And you had to curl up in a kind of pseudo-fetal position in order to look out the windows, and then sit up and take notes, and lots of moving around, which was a lot of fun early years, but later years I found it a little more difficult to do, and went to sea with a number of students who also have not sure what happened there. Sanjay, can you confirm that I'm back online? I briefly lost my computer. Hello? Sanjay, can you confirm that I'm... Okay, great. Thank you, all of you. Kamesh, I appreciate it. Mohit, I appreciate your feedback. What I wound up doing was imagining that if we had fiber optic cables extended out to the Juan de Fuca Ridge off the coast of Washington, Oregon, we could begin to transform the limits that were imposed on us automatically by having to stay inside the submersible a mile deep, 2 miles deep, or we had the option of using what we call remotely operated vehicles, which are very capable robots about the size of 2 Volkswagens put together, and they had manipulators and cameras and all sorts of things. And so in the last 10 to 20 years, remotely operated vehicles have begun to replace human-occupied submersibles as the workhorse of research into deep submergence issues, whether they're at the subduction zones where the plates are coming together, or whether it's spreading centers in either where the plates are pulling apart, or even on subduction zones where the plates are slipping past one another. All of these were quite viable sites for investigation, but the submersible, you were only in the submersible for about, on the bottom for only about 5 hours, and that was frustrating. So I worked with a number of colleagues, particularly at the Applied Physics Lab here at the University of Washington, and around the country at Woods Hole. Alan Shave was one of the colleagues. I worked with JPL folks, Pat Beecham, and a number of folks from a variety of places, including our Canadian colleagues who were at the University of Victoria. And we came up with the idea of what we called at that time Neptune, Northeast Pacific Time Series Undersea Networked Experiments, which involved fiber optic cables that were stretched across the Juan de Fuca tectonic plate and had a variety of both sensors and robots on them. That came to fruition in the Canadian effort in about 2007 to 9, and in the U.S. side, we had started the planning before 9/11, and it seemed to be delayed by some of our responses to 9/11, the event in New York City and Washington, D.C. But since 2009, the University of Washington Oceanographic Department of Oceanography, and the Applied Physics Lab teamed together as part of the Ocean Observatories Initiative, funded by the National Science Foundation and overseen by the Consortium for Ocean Leadership in Washington, D.C. We literally, from 2009 to 2014, we built a cabled observatory which comes offshore. The cable comes out from Pacific City, just south of Astoria in Oregon, and stretches about 400 kilometers across the tectonic plate, and it's about maybe 250 kilometers is another strand of cable coming out of the same location, Pacific City. Goes down the continental slope, turns south gets to the latitude of just off of Newport, Oregon, and then climbs back up the continental slope. And a number of experimental sites are located in that subduction zone complex, or the Cascadia complex, accretionary prism, whatever your terms are. And that was finished in 2014. Since that time, data has been streaming from approximately 120 instruments and robots that are on that system, and it's been streaming ashore continuously. And in the last month, our colleagues from Rutgers University, under the guidance of the Consortium for Ocean Leadership and the support from the National Science Foundation, have in fact made available, and if you search on Ocean Observatories Initiative, you will find the website and get access to the data that is flowing from those networks. One end of the network is out on the spreading center, the place where Juan de Fuca Ridge, where the plates are pulling apart. On top of the spreading center is a feature known as axial seamount, which is a very restless and now wired volcano, and there's a story to be told there. We had some excitement with that not long ago. And we are also looking in some detail at various portions of the subduction zone complex, or the accretionary prism complex. A couple of those experimental sites on the seafloor connected by the cable are focused on the gas hydrate deposit at Hydrate Ridge. Another experimental site is on the seafloor deep at 2,900 meters at the base of the slope. And another one is up at 600 meters and is the beginning of a coastal oceanography component of the program, which was conceived of and designed and built by our colleagues at Oregon State, but it is connected to the fiber optic cable. So there are various portions of this Ocean Observatory Initiative that are connected to the cable, and other portions that are not. And I urge you to look at the website, Ocean Observatories Initiative website, and to gain more background and information about that. Most recently, from a scientific point of view, and certainly from an astrobiological point of view, we had the excitement in April of this year, first of having a workshop, which, gosh, I invited about 100 people, expecting maybe half of them to show, and 90 people showed up for that workshop in April 20th to 22nd. And the focus of the workshop was knowing from the work of Bill Chadwick and Scott Nooner that axial seamount was very restless, and the seafloor inside the caldera on top of the volcano, on top of the ridge crest, was rising at about 15 centimeters a year for a long time, and then suddenly in 2012 it began to rise at 60 centimeters a year, which made everyone both excited and a little bit nervous that the volcano would erupt. So our workshop in April 2022 was focused on what do we do when the volcano erupts. It was predicted to erupt within a couple of years, I suppose. And, the upshot of that workshop was we had grand plans as to what we would do and all the things that would happen. And then 2 days later, the volcano erupted, and we were able to track William Wilcock and some of his colleagues, and we were able to track the earthquake activity. And Chadwick and his colleagues were able to track the deformation in real time of what went on as the volcano erupted. The seafloor dropped inside the caldera, dropped about 2.4 meters within about 12 to 18 hours. And the earthquake count in and around the volcano, in and around the caldera, went from somewhere in the vicinity of a couple hundred events per day to something like many thousands per hour for almost a day. And then the earthquake activity died away. Well, it turns out the eruption took place there, and there were some very unusual acoustic signals, we call them impulsive events. They were not earthquakes, but they seemed rather to be explosions. And Maya Tolstoy, Will Wilcock, Charles Garcia, a number of folks began looking at that. Jackie Auerbach was looking at those, and they concluded that they might be related to an eruption of some sort, which was different than anything we'd seen before, because no one had ever recorded an eruption of an underwater volcano like this. And sure enough, 3 or 4 months after the event, in July and August of 2015, scientists from the OOI program, the Ocean Observatory Initiative, as well as NOAA and a number of their colleagues funded by the Moore Foundation, used an NSF cruise to actually get out and look at what had happened back in April. And they found lava flows in the caldera. They found lava flows well to the north where these strange noises were coming from. And they took samples, and they are working up the samples at this point. So what I suggest for the ocean, for the astrobiology community, is that this opportunity be turned into a natural laboratory in which any number of experiments and studies of live hydrothermal systems or very lively gas hydrate deposits, which are venting methane continuously, but in a pulsed manner, but continuous over month to month, in a pulsed manner from the subduction zone, that these become sites where folks with an interest in extreme forms of life, either high temperature forms or forms that maybe are associated with gas hydrates, begin to develop experiments and experimental approaches and possibly robotic systems with novel sensors that can be connected to the cable on a routine basis but not continuously, and that these analytical capabilities and mobile platforms and experimental sites actually be designed for deployment ultimately off-planet in places almost certainly we will find life. If we're going to find life, we'll find life on planets that have liquid water, probably oceans like Europa, or possibly Enceladus. Not sure we have an analog to Titan, but we definitely have a water ocean that's somewhere between a couple 100 meters deep to 3,000 meters deep. It doesn't match the 100-kilometer deep European ocean, perhaps, but the experiments, the analytical approaches, the artificial intelligence, the approaches that one might take to begin getting information, collecting information about what's going on beneath the ice and other systems is exactly the kind of thing that we think would really be excellent. So let me. So in a nutshell, that's what we've done over the past 6 or 7 years. It took about 18 years. It's a long time getting this thing in place and getting it going. But it is paid for by taxpayer dollars. It's in place. It's operating. The data is flowing ashore. You can take a look at it by going to the OOI and the Rutgers sites, searching on them for OOI information. And you can begin conceiving and thinking about ways in which this type of system might be useful for your own research because NSF has now invited additions, either funded by NSF or funded by other sources, additions that might actually be innovative approaches to looking at remote life forms using the cable. Now, there's one last thing I want to mention before we open for conversation, and that is that the cable has unbelievable bandwidth. It's tens of gigabits per second bandwidth, and it also delivers a lot of electrical power, and that both of those capabilities distributed throughout the volume of the ocean on the seafloor and up into the overlying water column are very powerful ways of being present offshore without having to be there. It is also true now that thanks to the work of Norm Farr and others at Woods Hole, we now have the ability to use optical modems underwater to transmit a significant amount of data. Electromagnetic radiation does not penetrate the ocean very far, but it is possible to use optical modems to communicate at least at the 1 to 2 gigabit per second bandwidth within 5 to 10 meters of one another. And that opens the potential for having very innovative mobile experiments that can come back to a docking station or a garage and plug in, upload more power, basically charge batteries, whatever, and download massive amounts of data, even HD video that has been collected by that mobile platform. So with that vision in mind, I think I'll stop for a bit and see if there are any questions that pop up on the screen. Hello, can you confirm that there's anyone out there? Okay, Sanjoy starts, diving in Alvin submarine is probably the closest one can get to exploring another planet. Could you describe a little bit what you felt and what you saw? That's from Sanjoy, and I just got another one from CB Singravelu, and I will answer that one in just a second. But to address the question by Sanjoy, the submersible is on the back deck of a ship known as the Atlantis, and it is a 17-ton submersible, the essential component of which is the titanium sphere, which is about 6.5 feet in diameter with windows. There's a new version that the Woods Hole Oceanographic has put together. You are on board the ship, and in the morning you get up early. You get out on deck and enter the submarine. It's on the back deck, ready to be launched with a gigantic A-frame, which is a crane that can move forward, pick the vehicle up off the deck, and then it moves aft, backwards, off the back deck, and can lower it into the sea. At that point, once you're lowered into the sea, and all the hatches have been closed before that happens, of course, you are then released and you are free from the ship. There is no tether connecting the submersible. There's last-minute checks, and then you blow the ballast and you begin to descend to the seafloor, which at about I don't know, it takes about an hour and a half to get to the seafloor if the seafloor is 2 kilometers down. And so you get to the seafloor at about 9:30 and you start working, and the batteries last for almost 5 hours and maybe sometimes 6. And so you ascend about 3:30 or 4 in the afternoon, depending on how demanding the dive has been. In the meantime, you have been able to take photographs, you've been able to look out the window, you've been able to take video, you've been able to take samples of anything there. There are 2 people in the submersible, 2 scientists, and then, sorry, there are 3 people. One of them is a pilot, and they seem superhuman sometimes. And then there are 2 observers, and the observers are usually scientists, not always, sometimes reporters. And we have had, I think by now they're probably pushing 5,000 dives in Alvin, and there has never been a serious accident. Certainly no one has died. There have been 1 or 2 accidents during a launch that might have broken a leg here and there, but it's now a very, very safe and very routine approach to dive in Alvin, and it is an unbelievable experience. I vividly remember my first dive in I think it was around June 4th, 1980, south of the Azores on the Mid-Atlantic Ridge. and I was glued to the window the entire way, actually watching bioluminescence all the way down and all the way back, and spending my time as a geologist, which is my main field. I was captivated by, of course, the volcanic terrain. We settled into it about 4,000 meters depth. So that's a short little answer, maybe not short enough for some of you. Sanjoy, that's my best response. And the question from CB, I've read about a similar happening in Jupiter's moon. They described about something called serpentization and how it helps us in letting us know about presence of life forms. Can you please tell more about that? CB, there are two parts to that answer. One of them, referred to probably earlier by my colleague John Paros, it dealt with the discovery some years ago of lost city, which is the term used to describe a very unusual hydrothermal system. It was first published on by Deborah Kelly, so you can search on Lost City Deborah Kelly, and you'll find some of those early papers. The discovery was on a cruise that she was chief scientist on, and it was not the black smoker sulfide intense systems that we are so used to in terms of the 350 plus hydrothermal sites that have been found all around the world's mid-ocean ridge system. But this was off-axis on the mid-Atlantic ridge, near the Atlantis fracture zone. And it was off-axis on an area that was an uplifted, what the geologists call a massif, which was a large underwater mountain. And the rocks exposed on the mountain were very primitive rocks, deep within apparently had come from deep below the oceanic crust and had been exposed by tectonics. And there were gabbros and periddotites and carbon deposits. There was a lot of CO2 streaming off the system. And it formed, instead of pillars of sulfide, of chalcopyrite or pyrite, it formed pillars of carbonate. And those pillars of carbonate were in some cases 8, 10, 15 stories tall and are just elegant spires. And the composition of the fluids coming out of those systems was very basic. It was not very acidic. And the implication was that there was serpentinization, that is the reaction between seawater and olivine minerals, to create serpentinite, which is a hydrated version of magnesium silicate. And in doing so, there was heat released, and that heat caused the circulation, and the circulation and the reactions caused the warm fluids to rise, rich in CO2, and to deposit these materials. Well, some of the chemistry of what has been detected in the venting from Enceladus, some of the chemistry in those fluids venting from Enceladus seems to be similar in some regards to the chemistry that was measured for Lost City directly on the seafloor and in the laboratories. So there is some sense that life may have originated on other planets as a result of the interaction of seawater and periddotites, which are olivine-rich rocks from deep in the earth. And that instead of being hydrothermal vents, which are typical black smoker producers, 350 degrees centigrade as the hottest fluids, and salinity is really close to seawater unless they have boiled, with the pH or the acidity they're very, very acid fluids, even at those 300-degree temperatures. So those are there's a dichotomy between the two kinds of hydrothermal systems we've seen on this planet. And some people think that Enceladus, not a moon of Jupiter, but Enceladus, um, around Saturn, may actually have similar systems, and it's possible that that Europa does as well. That's the best I can do on the spur of the moment on that one, CB. Please contact me if you would like more information, and I'll put you in touch with other folks. Mohit Melwani Daswani has the following question. You mentioned using remote submersibles versus diving manned submersibles. For Mars, for example, we're hoping to ultimately send field geologists because they offer several advantages, or do they? Good question. Over remotely driven robots. Could you say something about why we use remote submersibles? That's a very good question, Mohit. There will always, I think, in human exploration, there will always be the dilemma of, do we send increasingly capable robots or do we send human beings? The cost, well, the presumption underlying the deployment of humans to other planets or even to the seafloor is that we want to bring them back alive. That is a valid assumption in my assessment, and the guarantee to deliver such capability is that you have to spend quite a bit of money in order to make sure that that lives are protected. I keep letting my screen go dark because I'm sorry. Anyway, so the really fascinating point on this issue, Mohit, is that the trend is for robotic systems with all sorts of instruments on them, also connected to the ship, I might add, so that you're operating the robotic vehicle from the ship at the surface of the ocean, and you have a fiber optic connection with power, and it goes over the ship and down to the seafloor, and the ROV, the remotely operated vehicle, is attached to that. And the pilots are actually on board the ship, and the data flows up the fiber and is constantly logged. All the video, everything is logged, even the location of the samples and the kind of labeling of the samples. Everything is done remotely, but it's done very well, and you can use these things 24 hours a day, unlike the submersibles, which are quite limited. Now, if we send, you've asked the question of why robots instead of humans, and there are divided opinions on this issue of whether a seasoned geologist, geophysicist with lots of field experience would be a better investment to go to Mars or any other planet for that matter, and I suppose eventually Europa, although Europa is a singularly deadly place in terms of the radiation climate, the temperature, and the vacuum. You'd have to get into the ocean quickly, and that would be a little awkward because we're not designed or adapted very well for being underwater as humans. So robots seem sensible there, whereas you're quite right, it's possible, particularly given the movie recently come out, it's possible that we could send human beings who would have the capacity to innovate and the insights to observe and interpret a lot of the formations on Mars. My personal opinion as an oceanographer, of course, is that a planet with an existing ocean on it is much more likely to have extant life forms on it than a planet that may have once had an ocean 3 billion years ago, like Mars. But I concur entirely that Mars is a fascinating, absolutely fascinating place, and it has a lot of volcanoes, and it's really it's almost certainly one of the planets that we should be exploring. So the one last thing I want to say is that robots are rapidly becoming much more capable. Artificial intelligence of various types is moving in leaps and bounds. The ability to communicate to, say, an underwater robot on Europa would have a very long time lag. So there would have to be a considerable amount of onboard intelligence and the ability to also transmit through the ice and then back to Earth. And there are a lot of complexities there, I have to admit. Either way, on Europa, neither robots nor humans would be a foolproof approach. They both would have their own problems. Okay, so that's about as much as I can address on that front at this point. I don't know whether that satisfies you or not, CB, but get back in touch, or Mohit, if there's more that you'd like to know. Okay, it looks like Sanjoy has provided a website for Lost City with a nice picture of Alvin, and Mohit comments, and CB says thank you very much. Then Kamesh Narasimhan has said, can you tell us about the most fascinating sea life that you encountered, like microbes or viruses with unusual DNA that was collected, or like fluorescent animals that you could take as a pet? I'm not likely to go down the pet path. There are others who are much better, I think, probably at addressing the microbial and viral denizens of the deep. But let me just simply say that I think the early work by John Paros and many of his microbiological colleagues has been very exciting, and the idea that there is a deep, hot biosphere below the sea floor associated with submarine hydrothermal systems, and probably hydrothermal systems anywhere on the planet, is absolutely fascinating, and may well have been the areas in which life originated on the planet, because some of the life forms seem very primitive. Having a microbial pet was not something I had ever thought about until your question. The fluorescent animals, the biofluorescence, or the bioluminescence, I guess is the best way to put it. From the work of Edie Widder, Widder. I have come to understand, although I'm by no means an expert, I refer you to her work. She has an outfit called Orca. Search on Edie Widder Orca, and you'll find a lot of information about bioluminescence, which is totally fascinating. It is, of course, below the depth to which sunlight penetrates in the ocean, which gets, we think, maximum penetration maybe below 200, maybe 300 meters, and at the most simplest wavelengths, maybe, or the last wavelengths, maybe 500 max. Below that, which is where most of the mid-ocean ridge activity is, we see bioluminescence in terms of the animals, and I understand that my information is a bit out of date, but I understand that there are something like 32 ways in which life forms on this planet have developed the ability to create bioluminescence, which is their way of signaling in one form or another. It may be sexual signals, it may be protective signals, it may be ways of attracting others. There are many different reasons. Fireflies are, of course, something we all know about. But in the ocean, below the penetration of sunlight, it is a major pathway for communication, and it's very subtle, and we do not speak that language yet, although I suspect Edie and some of her students, colleagues, and successors will try to learn how to use the bioluminescent language. Okay, so let's see. Sanjoy Paros was a guest. Talk with an astrobiologist. You can check that. GM OM Allen, or is it Allen? Allen. If you were to identify the most pressing technological basic scientific challenge that would open up greater avenues for observation and experimentation, what would it be? Along those lines, what would your dream experiments be that you would like to run if you were given unlimited resources to do them? Thank you very much for that grant, or that question, if not the funds to fulfill it, Dr. Allen. Personally, I think the most challenging aspects right now in the world of oceanography, and I'm of course very interested in submarine hydrothermal systems and all the implications for both life on planet as well as early life on this planet and possibly life on other planets. In addition to that, we must not lose sight of the fact that the ocean on this planet is in fact fundamentally our life support system. Every other oxygen molecule that you breathe comes from phytoplankton production in the near surface of the ocean. So the ocean plays a critical role there. It also absorbs and releases both atmospheric chemicals in the form of greenhouse gases, as well as heat, which, and certainly at the high latitudes, other portions of the OOI system, by the way, are focused on making measurements of fluxes at high latitudes, where the winds are always high, the waves are always intense, and the exchange between atmosphere and ocean takes place routinely. So the experiments that I find most compelling would be the ones in which we can look at entire ecological systems, which might extend over many cubic kilometers, and to begin to study them from within so that we can look at 20, 30, 40 variables in both time and space, and we can link that information in real time to models of those ecosystems in the ocean. Remember, the ocean actually supports everything that it physically supports everything that it chemically and biologically supports. It's unlike ecosystems on land, which tend to primarily be located on the surface of the Earth. You know, at the rock-air interface is where most of the biology on land is found. Even in rainforests, it's only a couple hundred meters layer on top of the rocks and beneath the atmosphere. Whereas in the ocean, all the biology, all of the chemical changes, all the physical parameters and the movement, it's constant. Everything is moving with respect to everything else, driven by one thing or another. And the support for any life form can actually come from the surroundings as opposed to through the root system. So it's a very different and not necessarily intuitive ecosystem, and I think it's extremely important for us to spend a lot of time looking at, in 4 dimensions, at the multivariate characteristics of these marine ecosystems, because we are dependent upon them for oxygen, for scrubbing the atmosphere, for many different parameters, and of course for food as well, and probably eventually for pharmaceuticals, which I think will become the oceans in all of their complexity will possibly become the next rainforest where we recovered a lot of drugs much earlier in the history of medicine. So that is my sort of fantasy experiment, would be to constantly be able to have maybe thousands of robotic systems with tens and tens of different kinds of sensors, physical, chemical, and biological sensors on each one of them, all communicating in real time at the speed of light, and all communicating with those of us on land who are operating computer systems to actually put enough data into our models of how these systems function so that someday, maybe, perhaps, we can become predictive in terms of how the ocean does now and will in the future behave. That's a very controversial point, I might add. This business of geoengineering is highly controversial, and it's I suppose the way to phrase it is, it draws passions from both sides of the argument. Some people think it's foolish for us not to be experimenting to find out how the ocean and atmosphere system work. Others feel that we are not wise enough to do it carefully, and therefore may do more harm than good. It is a very controversial area, and yet, personally, my perspective is we are running a gigantic experiment as a human race ever since we started the Industrial Revolution. We've been converting massive amounts of sequestered carbon in the rocks we've burned the fossil fuels, and we've released massive amounts of carbon back into the atmosphere. It may have taken 200 million years to sequester, but we've released much of it in 200 years. So that is an experiment. Like it or not, we're running the experiment. Sadly, we are very inadequately monitoring the results, and indeed, many folks in various portions of our society don't even believe there's an issue. So that's a topic for perhaps another forum. That's about what I can do right now. I can't quite read it. It looks like O.M. Allen. So Mohit is back with another question. Thank you for answering. Just a quick follow-up. Why not just cache samples to return them and analyze them in more capable Earth labs, rather than relying on more limited analytical instruments in remote vehicles, both for planetary and ocean missions? That's a great question, Mohit. In fact, we should probably be doing both, and I would call to your attention the work that has recently been done by the director of the Monterey Bay Aquarium Research Institute. They have developed a capability known as the ESP, the Environmental Sample Processor, and it has the capacity to do at least rudimentary DNA analysis with captured samples that can be run on site, and if this type of thing were attached to a cable, the data would be sent back ashore from this remote lab or multiple labs, and would be available again through a fiber optic cable. And the experimental techniques could actually be run. Remember, many of you have probably forgotten what happened on 9/11. Not forgotten what happened on 9/11, but on 9/7 in 2001, some doctors in New York City removed the gallbladder of a woman who was physically in France. Now, if they could do that almost a decade and a half ago, using remote robotics and high quality communications, how much more could we do now, and at least in our own ocean, at the end of a fiber in a laboratory offshore? We could do probably everything remotely. So we have both remote analytical capability and we have interactive analytical capability available to us, at least on Earth here. What we could do on other planets, I think we should do as much as possible remotely, and that should then guide further sampling and sample return if that is financially and politically feasible. It's the other side, of course, is you never know when you're bringing life forms back from another planet, you never know what you're introducing to Earth. So there may be objections from a number of quarters as to whether or not we should bring potential life forms back from other planets. And of course, the reverse is also true. Should we be entering ecosystems on other planets without doing everything possible to make sure that we protect what might be living there from what might be living here? That's the end of that question for you, Mohit. I don't know if I've adequately dealt with it, but let's see. We have another from Sanjoy. Have you benefited from mentoring in your career? Could you please speak to that? In my career, I've been mentored by a number of folks, ranging from undergraduate time at Lehigh University, where the faculty was excellent. It was actually in the period before plate tectonics was fully accepted. This was in the early 60s, but the faculty there and much of the faculty at University of Arizona, particularly one or two of my advisors, a fellow by the name of Spencer Titley, who was a mining geologist, is still alive and well and in Tucson. So he was very helpful. And when I came to the University of Washington, I had folks like Ross Heath who were giving me insights and guidance. He was our dean for a while. And I also worked with a number of colleagues from Woods Hole. Several folks were extremely helpful to me in terms of beginning to frame what I was doing. Then, during the development of the Ridge program, I think I might have been mentored by colleagues who were younger. I was actually probably mentored by my interactions with a lot of students, in a sense that the flow is both ways, and that has been excellent. So there's lots of possible sources of mentoring, both scientific and philosophical. Dr. Allen says, "Thank you for your passionate answer. I wish I had the power to sign off on a grant like that." Well, I would be happy to discuss, at least discuss the topic. I think it's up to me to find the funds to pursue that. But I might add that I think perhaps what's most important is that we now have the ability to be present, very present, remotely, not just in one location, not just with one camera, not just with one manipulator or a sampling device, but we can be present with many sensors distributed through entire volumes of the ocean. So the questions we can begin asking can be fundamentally different kinds of questions, and the answers we can expect should expand and evolve as well. I think the other thing is that the delivering unprecedented electrical power and almost unlimited bandwidth to first order into the volume of the ocean is a gigantic invitation to many, many bright young people who are looking for the boundaries, to push the envelope on the boundaries of what we can try to do. If your imagination brings you to any particular point where you think that you might want to do something in the ocean, you can think about having essentially a laboratory of some sort, maybe a distributed laboratory or even a laboratory in which robots bring samples to the lab on the seafloor or up in the water column to do things that no one had ever thought about before. So it's an invitation to use your imaginations is the best way I can put it. Sanjoy, I think I'm seeing the questions are beginning to drop away, so I will wait for about a minute, but I think we've probably reached... oh, Sanjoy, you asked another question. We're getting close to time. Do you have any final words of wisdom for early career scientists? What do you do for fun? Oh, let's deal with the first one first. I think if I were to say anything to early career scientists, I would say science is captivating, absolutely fascinating, but it is not your full culture. Do everything you can to begin to understand the fullness of the culture that you're a part of, and remember how the ocean has influenced our culture in powerful ways across the entire planet. And I will leave you with a wonderful poem by Pablo Neruda. And that poem is, Pablo Neruda was a Nobel Prize-winning Chilean poet who wrote a poem named by the name of It Is Born, talking about the regeneration capability of the oceans. And that poem is very short. Here I came to the very edge, where nothing at all needs saying, and everything is absorbed by the weather and by the sea. And the moon swam back, its rays all silvered, and time and again the darkness is broken by the crash of a wave. And every day on the balcony of the sea, wings spread, fire is born, and everything is blue again, like morning. Thank you all for listening. It's a pleasure chatting with you. I would happily exchange emails with any of you that want to follow up. Take care, and thanks to you, Sanjoy. Bye-bye.